This is my DIY CNC machine. It's pretty good, but could it be improved?
Oh, here we go.
What? Welcome back to the workshop. So in this video series I'm building a CNC stall detection system, so hopefully I don't break any more end mills. And the next PCBs have arrived from the fab shop, so we'll have a closer look at those, explain how they work in a bit more detail, start fitting some of the components and do some checking and testing and make sure they work. And then to be able to mount this onto the DIN rail, I designed this little custom bracket. So we've got this clip on here and that snaps nicely in place, and then we can fit the control unit in the cabinet. The rest of it, yeah, there were some issues. Doesn't seem to work. Okay, as you'll see, we've got two boards here. So I decided to split it up, so one will be for the display, and then the main processor and all the electronics will be on here, and that will allow us to have the screen somewhere remote. So this can be inside the enclosure, and then we'll have a harness coming out somewhere on the front of the enclosure or somewhere a little bit nearer the user, and then you can press the buttons. But well, let's see, hopefully it'll work. I'm just again really impressed with the quality. I mean, you struggle to do that at home, I think. All the little silk screening, the masking, the little wires in there. I think about 4 or 5 wires in this design. Silk screening on the reverse side. Looks really nice. Little holes and everything. So, alright. Hopefully there's no mistakes, but I guess we'll find out in a few minutes. So I think the next thing to do is to start populating these and see if this new system's going to work. Alright, so I've got some IPA here. I'll just go that. Bit of a spray. Using this as it does evaporate. Actually, before it goes on that board, let's just check. Make sure we're going to be alright. So I think we'll put it in there. And then this is the top. Yeah. That'll come out the back and then it can go into wherever. Alright. Right, before we go too much further, we'll just check we've got continuity. 5, 6, 7, enable, reset, 5, ground, and keypad. Right, and to the 5, 6, 7, enable, reset, 5, I think we've probably just done that, haven't we? 5, yeah, ground, keypad, oh, keypad, oh, it's under there. Nope, what's going on? Oh, great. I missed a trace. What the... Oh, it's over there. Okay. First screw up, maybe. Oh. Ah, of course, right. So this unit here takes in 5 volts and it puts 5 volts out the keypad. Now the previous unit that I built, that went into one of the pins on the ESP32 and it was okay. I did check the voltage actually after I realised I shouldn't put 5 volts in, so thank you for those comments. Should be 3.3. It was actually putting in 3.9. Now I did wonder if I'd get away with it, but maybe long term it wouldn't be a good idea. So yeah, I've got this these resistors to make a voltage divider, so the keypad will come off one of those. Well, let's just find out which one it is. Okay, comes off, okay, probably the middle of those two. Alright, yeah, so I forgot about that. So good, back in business. Alright, so far so good. So I think now we need to make the spacer and then put the screen on, and that's it, because I'm just going to use the connector on this side. Alright, looking good. Alright, so just put those two resistors in. That should make a bit more sense now. I guess what we can do is reference it to ground. So we should see all of it, I guess there. Yeah, so we've got 3. Is that in short? Yeah, 3 ohms. I think the center tap might be that one. Oh no, that must be the end tap then. Okay, we've got 2 across that one. 2 there. Nope, that's our center tap there. Alright, it looks good. Okay, where were we? Yeah, we're going to 3D print that, and then we'll get display mounted. Okay, so you might remember last time I made a bit of a mistake with the spacing. This time I made sure I didn't make that mistake, and you can see I've offset them slightly, so that's sort of a 1.5 pin spacing there. As you can see, it all goes together. So instead of that mistake, I made a completely different mistake, which is last time I was on these header strips, and because I'm only using so many of these pins, now I'm mounting direct to the board, I haven't got enough holes and the pins are sticking through. So the ones I'm not using, these 4 here, I've just desoldered those, and then the main ones are there, so that's okay. So if I do revise this board, I need to put another 4 holes in just to allow those to stick through. And the other thing you can see in there, that white bit there is our 3D printed spacer, and then I've just got some holes in the board and some little pegs just to hold it in place. You see that one? Only half a peg there because it's right next to some of the little pins that are sticking through. So that, once that's soldered in, should give these, oh yeah, nice and solid feel and not bend the board. Before we go too much further, I'll just flash the code on here and just check these pins here, these test points, that we get in the voltages we expect. Just upload the code. Okay, can't see that board, can it? Okay. That's this one. Okay, that should be it. To 5 volts. Yeah, 3.3. I don't think these will work yet. Probably be 0. No, okay. And the other one we can check is if we've got 5 volts over here, the other side of the diode, which we have. And have we got 5 volts going to the sensor, which we have. That's probably about all we can do for now. So as before, we've got the relay soldered in, the flyback diode. I'm out of the transistors, so I'll have to order some more. And annoyingly, I'm out of the 1K resistors. I thought I had some, but nope, they were slightly different value. And the 2 resistors there, again, I need a 1K for that. And like last time, I've gone for the little plug-in for the chip, or chip carrier there, just in case we have any issues and we can swap that out easily. While we're here, we'll do the LED as well. So short one's negative. Just give these a trim. Alright, looking pretty good now. So while we wait for those resistors and the transistor to arrive, we'll just put all the sockets on down here. So these are 3.81 millimeters apart, and they should, you might just be able to see, they've got little features on there. I mean, they kind of slide together. They're a bit fiddly. There we are, like that. So I need 6 of those. Okay. Oh. That's not going to work. It's like The pin spacing is okay, but the gap between each one is different. How are they different to the last? Let's just put them there. Yeah, they're smaller, but the pin spacing's okay. What? These are a different brand, but I assume they would still fit. Okay, no matter, they'll just have gaps between them. Alright. So I'll solder them on like that. Alright, so I made good progress. As you can see, most things are on there. The only ones we've got missing are there's a 1K resistor there, which is for the e-stop relay. We've got the 1K resistor there, which is on the VFD circuit, and the transistor there. So I've got those on order. They'll probably be here in a few days' time, but I'm quite keen to press on and make sure this works at least. So I glanced at my stock the other day and I just saw that, you know, it was in the box like that. I thought, oh, I've got loads of 1K. Oh, actually it's 1.3. Now I just had a look at the circuit diagram, and that one there is the current limit for the transistor. So we're not using it as amplifier, we're just using it as a switch. So hopefully that'll still be okay with enough current to trigger that and trip the e-stop relay. And then the other one is on the 10 volt optocoupler circuit, which is from the PWM, so for the BFD, sorry. And all it'll mean is that this LED might be a little bit dimmer. Hopefully the pulses are still strong enough to trigger the optocoupler there. So that's one thing. And then the other one is the transistors. So they're supposed to be 2N2222A. I haven't got any left, so I've only got these, which are BC337. I did look at the spec of these and compare them, and they're pretty similar, especially for what I'm doing is just a switch. The only thing to note is the emitter and collector are the other way around, so I'll just have to be careful and put them that way around on the board. So before we can plug this in and test it, we need to make up our connector here. This is the JST-PH. These are the 2mm spacing ones, otherwise we won't see anything on the screen. Alright, so let's go and make that cable up and then we can give it a try. Now, maybe I was looking in the wrong places, but I couldn't find a cable that had this on the end. That's a JST-PH, the 2mm spacing, and also on the other end as well. So this connector, it's the same connector. But I did manage to find them with these solder on ends, so I've got quite a few of those. Connect that in there. Okay, looks good. Okay, so ultimately I want to be able to mount this onto DIN rail in the electrical cabinet. So it'll sit like that, and then the screen will be outside somewhere on the main control panel. This will be buried away. And obviously to do that I need to make some adapters or some brackets. So I iterated quite a few different designs and I came up with, I think these are the latest two. Look like that. And so the board goes on here and then the DIN rail clips into there, and then they've got this little detailed catch here. So that bit there is basically acting as the spring, and then that is the catch that actually allows them to clip into there. And then you can get a screwdriver into there and then lever it against that little contact pad at the top, and it should hopefully be able to lift them off. So these will ultimately have the heat set inserts in them. I think M4 to match the board, but for now let's just clip those on. So that goes into there, and then just push down. Snaps on nicely, and same with that one. Get roughly the right distance apart. That snaps on as well. So hopefully you can see there. And they will slide, but I think once they're in the cabinet that'll be okay, and then to get them out again, just lever them back like that. Come off. Alright, so just got to put the little threads in there, and then we can mount those. Right, let's go and test this out. Alright, here we go. Let's plug it in and see what happens. Ooh, it's come on. Ooh. It's not happy with something. Got power. I'm going to do a pin out check. What have I messed up now? Okay, let's just go and get the multimeter. And before we do that, we might need to flash this. Okay, code's uploading. No. Okay. Let's see where we've gone wrong. Alright, let's see what's going on. First of all, 0. 5 volts. Okay. Reset. Should be on pin 5. Oh. 18. Oh, and enable is... Ah. Okay. That makes some sense. So as you can see in the LCD definition, I've got two versions of it. One was this one, which is for chip 3, the previous build, and then for chip 4 I've done some pin out testing earlier, and 5 and 18 were reversed. This is all okay. The initial checks I did were actually wrong. So all I need to do is swap those over, comment that out, flash that in. Should work. Alright, let's try that. So we'll hook this up and then quickly flash that code in. Okay, I think we're back in business. Alright, let's start it up. Yes. I knew it would work. Alright, looking pretty good. And our LED is a little bit dimmer. Yes, it's not quite as bright because... Oh, it's alright though. Oh, and I've got my LED there from the spindle that's quite bright. Did I add that code? Oh, I guess I must have done. Okay, let's check the menu. Oh, is that working? Okay. That's too good to be true. That's on the... Oh, okay, so now I've got my little voltage dividers down here. It means each button press is probably giving a slightly different value. So they're between, I think 3.3 volts is 4096 units. Yeah, but of course it was expecting 5 volts before, so I might all be out. Alright, so what we'll do, we'll add a bit of code which just displays on the screen what button I'm pressing. And we'll write those down and then adjust the values in the software, and then hopefully the keypad will work. Alright, so we're displaying the values. So no keys is about 1790. Is that working? Okay. Left, not working. Down 630. What's going on then? Up. Oh, there we go. Up is about 1080. This is a new keypad, so maybe the keys are a bit stiff. Select. Doesn't seem to work. Okay, I've been playing with this for a little bit and I can't quite figure out what's going on. So each of these buttons has got various, you probably can't quite see them, but different resistors under there to give the different voltages. But when it goes through my voltage divider, something's happening. So rather than play around with that, I've got the original version on the bench and we can have a look at that one. Okay, so this is the previous model and I've just taken it apart and got it wired up like this so we can have a look at A0. Okay, so this is our setup. So we're powering the screen. We won't be able to see anything on it because I haven't got any of the connects at the top. So just putting our 5 volts in, and then the A0, that's the analog signal out. It's coming into the board, and I've just got a just a normal diode there. So it's just the 1N 4001 type, just generic one there. So that should drop it 1.4 volts. So let's have a look, and then we got that going into there. So let's plug it in and see what happens. Okay, nothing on the board as you would expect. And we've got our multimeter looking at volts. Okay. So that should be about 4. Alright, 4.4, and then the other side, oh, 3.8, still pretty high. Still a bit high to go into there. Right, I've been playing around with this a little bit more and I've come up with a bit of an odd configuration, but it does seem to work. So we've got our A0 signal, the analog signal coming out of there. We're just dropping it across, I think that's a 5k resistor, and then that goes to ground. And then we're just looking at the voltage dropped across that resistor, so that's A0 on one side and ground on the other. And with no keys pressed, you see we're at 3.2, so that's perfect to go into the ESP32. And if we press the button, so if we go select, it goes 2.3, go left, 1.6 down, 1.1 up, 0.48, and then right should be 0. Yeah. So yeah, let's just do that. Okay, I just found one more thing which I thought I'd share with you. So everything's off. We're looking at the resistance across that. I thought it was a 5k resistor, but it's 3k. However, it's 3k in circuit. So if we take our A0 off, which comes, there must be some other path around here through the processor to ground. If we take that off, so we're just purely looking across the resistor, there we're back to 5 again. Now if we put the screen and the processor in circuit, we drop to 3. So, I need to go and have a cup of coffee. Yeah, something resistors. Okay, let me bring up speed on where we've got to then. So I spent quite a long time with this board and determined that the switches weren't actually working for some of these, and that was giving some intermittent results. So I desoldered it, and then I thought about trying to repair those switches. I do have some spare ones, but in the end what I decided to do is to use the board off the first unit I built. So that's what's soldered in here. We know those switches worked because it worked before. Checked them before it went in, so that is now the second screen. I'll just order a new one, it's not worth messing about with that other board. And then the other thing I've done, you might be able to see down here, I've got that 5k resistor soldered in series with the output from A0, goes through there and then into one of the pins on the microprocessor. I might up that value a little bit, but for now it's kind of okay. So let me show you the values we get now. So just turn the multimeter on into volt mode. So I get that set up. I've got 3 grounds that give me lots of options. I'll put that there. And then where's the keypad? That's there. With nothing pressed at all, we've got 3.73 volts, which is a little bit high. It'd be better if it was 3.3, so I might be able to up that resistor a little bit and try and get a little bit more. I suspect the reason it's working with just one in line is because there's probably more resistors in here pulling it down or something like that, and I'm actually creating a voltage divider. Okay, so let's try this out then. So I've got 3.7, I'll just press left. Drops us to 1.9, press up, 0.5, down, 1.2, right, basically 0, I won't hit reset. Okay, if we do press select, we'll go into the menu, but we'll be able to see on there, drops to about 3, okay. Alright, so what I basically then did is looked at the Arduino units, which are up to 4095, for those different values, and I've put those in the software so it responds correctly to the keys now. So if we go into the menu, yeah, we can cycle through each one, no problem. You see it changing on there. We can actually change the values as well if we want. I'll just leave it as it is. Oops. Annoying if that didn't rock, and then come out. Alright, so as you can see, we're back in business. I'm a little worried about that, it's maybe a touch high, but we can use it for now and get everything else debugged. Okay, let's take a moment to talk about the pulses and the code and what the whole thing's trying to do, and maybe put it into context, some of the challenges as well. So I'll start in the middle actually. Let's do the VFD here, because this is the one that's running pretty quick, and then we'll come back to the spindle, which is running off the IR sensor. Right, so the VFD is putting out PWM or duty cycle signals, and the spindle is putting out pulses proportional to the speed. So the more pulses at any given time, the faster it's running, whereas on the PWM the pulses are the same spacing, they're just wider to get the higher speed. So the VFD, I looked at it on the scope, and it was running, I'm going to round it because it might be errors on my cursor, but I think it's running about 300 Hertz for the main sort of carrier frequency, if you like. So if that's our time window there, and then, yeah, okay, let's do another time window there. Within that frame, that was, I think it was 3 milliseconds. And that's 0. So, and then there's another frame, there's another 3 milliseconds, and so on. And then within each of those, try and draw it with a pencil so it's a bit easier. If it's running pretty slowly, you'll just get a pulse that's only like that, and then it'll do nothing for the rest of the frame, and then you get another one like that, another one like that, and so on. And so the amount it's on versus the amount it's off during that frame determines duty cycle and the speed. Alright, and note that that is 3 milliseconds, so it's pretty quick. As we go faster, so if we go in 12,000 RPM, then it will feel 50%, 50% on, 50% off, and so on. And again, that will the software reads how long it's on and off for, and it turns it into the speed. So straightforward. We'll come on to the fact that it's not looking at every frame in a minute, it's looking at a lot of frames. So to put that in context then, the spindle, I've got, rather than one of these that I just showed earlier, I've only got one of these white discs per RPM. You know, I found that this multiple one wasn't very reliable, but maybe I can do something about that in the future. So that is running a certain number of pulses, so it's spinning around. So yeah, let's draw it like this. So if it's going slowly, the pulse widths are, oh no, they will get, the pulse widths get shorter as well, but let's say you're going quite slowly, so actually it's quite a short one, and then there's quite a gap between that and the next one, and then so on and so on, like that. Bear in mind, this is 1 RPM, or 1 revolution, sorry, and if it's, you know, if it's going quite slowly, that gap between there and there is huge compared to this. So on this scale, it's like off the end of the chart here. So this is actually relatively slow. As it gets faster, two things happen. These pulses get shorter, but they also get closer together like that. So you get more pulses in a given time. and because it's running around faster, they'll be a little bit narrower as well. A bit complicated to draw, but the time base here is pretty long compared to that. I could probably work it out at a given RPM, but the fact is this is on a very different scale to that. Actually, let's work that out. So if we're doing, let's say, let's make the maths a bit easier, 600 RPM, so that's revolutions per minute. Per second, that is going to be 10 hertz, 10 times a second. So it'll be 10 of these pulses in a 1 second window, and then each pulse will be spaced, or 1 over that, isn't it? 1 over 10 or 10th, which is 0.1. So it's going to be 100 milliseconds between pulses, so between there and there, between one pulse and the next. So at relatively slow speed, that is going to be 100 milliseconds, hopefully I've done that right, compared to 3 milliseconds between these pulses. Obviously these are fixed, but hopefully you get the idea. Now obviously these get closer when you go to the higher speed, but it gives you some idea of the kind of differences that we're dealing with in the systems, and how when we then sample them and average them and bring them together, we need to kind of sort of try and get them to be similar in terms of response time. So yeah, it ends up being quite big. So if that's 100, then this frame length is, well, it's barely registers on there, so it's almost kind of doing that out of the spindle, whereas out of the VFD, sorry, whereas the spindle is doing one there, then one there, and one there. Yeah, maybe let's make those a bit even spaced. That's a terrible drawing, isn't it? Hopefully you get the idea. Very big difference in speed. Let's see what that looks like at 24,000 RPM. So what I'll do is draw that over here. So this is our 24,000 RPM, and again we'll draw our, let's do it like that, separate it out of it, RPM, and we've got our pulses. Obviously they're very quick and very close together now. But how close? Well, let's have a look. So 24,000 divided by 60 is going to be 400 hertz, so 400 times per second. So how long is each one in a second? So that's 1 over 400, which is 0.025 seconds apart, and then microseconds, 1, 2, 3. I've missed a zero. Yeah, the zero is just there, isn't it? 0.0025. 1 over that is going to be, times that by 1,000. 1, 2, 3. 2.5 milliseconds between each pulse at full speed. So now at full speed, we're approaching this, or pretty similar to this time window, but everything else we're on a pretty different scale. So how does that complicate things? Well, when we're sampling this and then trying to run some kind of average, this is where the compromises kind of need to be made, and you're a bit slow for that to make sure that that's going to be okay. So what we're doing at the moment is, you probably saw the, let's draw it down here. So let's say our spindle's running at some, spread it out a bit, something like that, some kind of mid-range speed. So this is our spindle, like that. And then the VFD is putting very closely packed together pulses on the PWM. And then we're going to take a sample. So I think one of the default settings I'd got, or one of the settings I got, was about 250 milliseconds. So let's say for argument's sake that takes you from there to, I don't know, somewhere there. That's our 250 milliseconds. This is all badly drawn, isn't it? But there's loads of those, and there's a few of those in that time. So in that time there, the software is looking at how long was it on for compared to how long was it off, and basically it adds that, so on. It adds up all the on time, and it adds up all the off time, and then it just does a ratio of the sum of those, also the on time divided by the sum of those, so that gives you a percentage, and then that percentage is mapped into an RPM to go between 0 and 24,000. Hopefully that's straightforward and clear. Spindle obviously is a bit different, there's going to be a lot less of those, but let's say we've got a couple of pulses in there. So in that time it will have counted how many on, so that's 1, and there's another one, 2, and so on and so on. So there might be a few more than that, but how many times did it come on in that window, and then that goes into like an array, and it's a moving average array, and you can say how many averages you want. That was one of the parameters in the software. So let's say we've got 5 of those. 1, 2, 3, 4, 5. Yeah, so just a standard running average. So it reads the first value, puts it in here, and then next time round it puts a value in here, and so on and so on, and it's always updating and adding a new field to this, overwriting the old one, and kind of getting this smoothed average. So as you can see, because it takes this one and then that value goes in there, takes the next one and that value goes in there and there, it's actually relatively slow to kind of keep up. Now it does kind of work because obviously a lot of these values are very close to the real one. It's just as it moves away, some of them start to move further away, but it will catch up, and the rate that it catches up depends on how many of these you've got. Lots of parameters come into play. So you can see it's actually quite slow, and therefore it's doing loads of VFD sampling in that ons and offs in that time, and effectively for this one it's then going to put that into another array of 5 units and 5 of those, and again do the running average of that. So this is where the comments come from, people saying, well, wouldn't it be better if we had a few more of these like this? Yeah, absolutely, we'd have a load more of these, and ideally we should be something on the scale of the VFD, and then we could do something a bit different and maybe make it a little bit more robust and much quicker. But effectively you've got to wait for these so you don't go too quick. You've got to put those in a moving average array, which you can vary the size with the user parameter. Same thing here, that goes into a running average, and you're ending up kind of saying this is your spindle RPM that appears on the screen, and then this running average is your VFD RPM that appears on the screen, and then it's comparing these two and seeing if they're different more than a specified amount. I can't remember what I put in the end, but it depends on the load meter, doesn't it? So if these differ by too much, and you are decelerating on the spindle, then I think there's one other check it does, then it throws an e-stop. So could this be better? Yeah, I think so. But what I might do is run it as it is, see how we get on with actually cutting some metal, and if I have to then play around with the software, so be it. That's relatively straightforward, because I think the hardware is probably good enough to go to the next stage and see what happens for real. Okay, I just want to talk about one more thing. So we talked about moving averages, where the values just go in and it allows the signal to smooth out a bit. The more you have, the smoother, but the slower it is to respond to the true state of the system. But it's a pretty popular technique, loads of it online, and that's why I went for it straight away, because it was worth trying. But it does have some downsides in that it doesn't react according to the actual speed of the system, so it's always running at the same speed. You've got your sample time and so on. Thank you very much for the comment on the Kalman filtering. So a long time ago I'd done some Volt Kalman filtering, but that was on motor orders. So if you've got 8 poles on a motor, you can extract 8th order, 16th, and so on and so on. But it was an offline processing technique, and it took a little bit longer. I don't think you could do it real time, so it was quite processor intensive. But this is different to that. There's just Kalman filtering, which in essence is a speed dependent filter. So it can vary the speed depending on how fast this thing's running, and maybe bring out a bit more optimization of the system. The mathematics is pretty heavy going. You need to understand about the state model. There are lots of parameters it needs to run. So if you want to read about Kalman filtering, I'll just put some references down in the description down below. And I thought about that, and I thought that's going to be a lot of code to get that up and running. However, people have been here before, and there are libraries for ESP32 that will take a few parameters and then it will do that for you. So it is something I might think about as a future direction, but this might be good enough, and it's one thing just saying, oh, there's a theory, there's an approach, there's whatever, but as I found out on many of my projects, when you're doing it for real, little details, little things that are true for your particular example make it harder. There's edge cases, there can be things that catch you out, so it'll probably draw me in and take a lot of time if I go into that. So I might leave it for now, but it's an excellent comment, thank you very much. Let's see how we get on with this, but if you're doing something like this, by all means have a look at the Kalman filtering as well, which is a little bit more adaptive, perhaps a little bit smarter than this. Okay, I think that's it for this video. I'm pretty pleased with the progress. I'm glad I made the decision to split the LCD screen from the processor so I could have that buried away in the cabinet and have the screen and the buttons somewhere a bit more accessible. So pleased with all that. A little bit worried about the the voltage going in there, so I might tune that resistor just to bring that down a little bit more, but we'll do that off camera. Some other good things is, yeah, the new board. Got that to work in the end. Bit annoying about the spacing of those different connectors down there. Just that different brand having the different layout. But anyway, so if you're enjoying this series, feel free to subscribe, add some comments. Good to hear what you think. And that being said, thank you very much for watching, and see you next time.